We're continuing with Chapter 1 of the College Algebra textbook, and in this video, we're going to go through Section 1.5, Applications of Quadratic Equations. Okay, applications of quadratic equations. This first section is talking about quadratic equations and geometry, so solving for something related to geometry. A trough at the end of a gutter spout is meant to direct water away from a house. The homeowner makes the trough form from a rectangular piece of aluminum that is 20 inches long and 12 inches wide. He makes a fold along the two long sides a distance of x inches from the edge. If he wants the trough to hold 360 cubic inches of water, how far from the edge should he make the fold? So you can see, you know it's 12 inches wide and 20 inches long. And then the volume is going to be 12 minus 2x. We don't know what x is. So 12 minus these two x's times 20 times x. You see that's the volume inside the trough. So if we come here, the volume is 20 times 12 minus 2x times x, and that's equal to 360. So you get a quadratic equation. We're going to work a bunch of examples, but I just want to go through the examples in this section to give you a preview of this. So they solved the quadratic equation by factoring and using the zero product property. There's a double factor here, like a squared 2 factor, so the only answer is x is equal to 3. So x should be 3 inches. Okay, in example 2, it says a window is in the shape of a rectangle with an adjacent right triangle above. The length of one leg of the right triangle is 2 feet less than the length of the hypotenuse. The length of the other leg is 1 foot less than the length of the hypotenuse. Find the lengths of the sides. So the hypotenuse we don't know, but we know that this one of the legs is 2 feet less than the hypotenuse length, and one of the legs is 1 foot less. Okay, and so we can write an equation using the Pythagorean theorem. If we do that, we get a quadratic equation. We get this quadratic equation. We solve it, and we get two answers. X is equal to 1 and x is equal to 5. So which one do we use? Well, you just inspect them both. One of them is going to be unrealistic. Maybe it's negative. Well, a side of the window can't have a negative length. Or 1 here, they reject it because, yeah, if x were 1, then the length of this leg would be minus 1, and the length of this leg would be 0. That doesn't make sense, right? So x is equal to 5. And this was tough for me at first because, again, it just feels like, is the math broken? It gave you a wrong answer. But I'm just going to tell you to try and think about this on your own. Math is just a tool. It's a man-made tool that we use to solve problems, okay? This gave us the answer to our problem. This is the problem. We have a window, and then there's a right triangle above the window. We know that one leg of the right triangle is or should be 2 feet less than the length of the hypotenuse. The length of the other leg, 1 foot less than the length of the hypotenuse. So what should x be? If we make x is equal to 5, we solve our problem, right? If not x is equal to 1, that doesn't make any sense. If we make x is equal to 5, we solve that problem that we have. That's what math is doing for us. The tool worked. This 1 just comes because the math equation, this quadratic equation doesn't know the problem. This is just a quadratic equation. It's just going to give you, it's a quadratic equation. It usually has 2 solutions. It gives you 2 solutions. This knows nothing about a window. So I hope that helped to, if you find this confusing, I hope that helps. If it doesn't, then just try and think about on your own why this happens. Okay, that was applications involving geometry. Here's applications involving quadratic models. In the study of physical science, a common model used to represent the vertical position of an object moving vertically under the influence of gravity is what? Right? This is the position function for an object under the influence of gravity. This is a quadratic equation. 1/2 times g, which is the acceleration due to gravity, times time squared, plus the initial velocity times time, plus the initial position. right? So don't worry about the meaning of this equation. You know, that's for a physics class or a engineering dynamics class. Just that's what this equation is. It gives you the position versus time for an object that's purely under the influence of gravity, like it's traveling vertically. If you throw an object up in the air, throw it up vertically, what's its starting velocity? We're neglecting air resistance. A lot of times you can do that. If you just threw a baseball up vertically as high as it could go, and you want to see its position versus time, in that situation, you could probably neglect air resistance, and you'd get this formula would give you a very accurate answer. But you know G is 9.81 meters per second squared. Time is just like the function variable. What's the initial velocity of the baseball right when it leaves your hand? What's the initial position? Is it 0? You know, you can put any initial position you want. It could be 0 or whatever you want. And you can find the position with respect to time. Okay? So again, that's a quadratic equation. And so it says here, a toy rocket is shot straight upward from a launch pad of 1 meter above the ground, right? So the starting position is 1 if you're measuring that relative to the ground. Relative to ground level with an initial velocity of 24 meters per second. Write a model to express the height of the rocket, S, in meters above ground level. So you just use that formula. We know the initial velocity, we know the acceleration due to gravity, we know the initial position. So that's what you get. This is a quadratic equation with respect to time because they plugged in V naught, G, all that. Find the time at which the rocket is at height of 20 meters. So, okay, yeah, what do? You set the height equal to 20 and solve for t. So now you have to solve a quadratic equation. Now this is interesting because if you come here, they solve for t and they get 2 answers. So I guess, all right, we're going to inspect both and eliminate 1, right? But none of these are negative. Both of these are plausible. And so this is tricky because, well, when do you neglect an answer and when don't you? It just depends. It's something you'll have to get used to with experience. But if both of the answers are plausible, these are both positive times, none of these are negative times, then that equation satisfies both of those answers. So you need to look and see, well, the equation says that both of these are solutions, so it should make sense physically for both of those solutions. And this is true because at 1 second, it's on its way up. At 3.9 seconds, it's on its way down. Right? We're assuming this is an idealized situation where the rocket goes straight up and straight down. Okay? C, the time at which the rocket is at a height of 40 meters. Okay, so same question, but we put 40 meters here. And the solutions, there's no real number solution to this. So the rocket won't reach 40 meters. You see how that works? So maybe like if the maximum height, so it's going to get to its maximum height, then start coming down. And that's going to be below 40 meters. But at that maximum height, it's going to have one time where it's at that height. All other heights below that, there's going to be 2 times for each of those heights where it's at that height. Okay, so that's a preview of these word problems involving quadratic equations. Now let's work some problems.